Numerical number 8. Calculate the equilibrium number of vacancies per cubic meter for aluminium at 500 degrees Celsius. The energy for vacancy formation is 0.75 electron volt per atom. Atomic weight and density of aluminium is given. Atomic weight is 26.98 and density is 2.62 gram per centimeter cube, and this atomic weight and density is at 500 degrees Celsius. So first let's write what are the given quantities. Given quantities, the temperature is given, which is 500 degrees Celsius. You have to convert that into Kelvin, that is plus 273. So it is 773 Kelvin. Second quantity, given quantity is energy for vacancy formation, and that is 0.75 electron volt. Similarly, atomic weight is given, which is 26.98, and density is 2.62 gram per centimeter cube. These are the given quantities. We also require Bohr's constant to solve this sum, and Bohr's constant is 8. Boltzmann constant is 8.62 into 10 to the power minus 5 electron volt per Kelvin. The formula to solve this sum is NV. NV is number of vacancies, that is equals to Ns. Ns is the number of atomic sites available, into exponential of minus EV by kT. So this is the formula. As you can see here, Ns is not given. Ns is a number of atomic sites, is not given. And number of atomic sites we can find by the formula rho into Avogadro's number divided by atomic weight. And therefore rho is known, which is 2.62 gram per centimeter cube, into Avogadro's number 6.023 into 10 to power 23 per kg per gram mole. We are considering NCGA system, divided by atomic weight, which is 26.98. And this is equals to 5.85 into 10 to power 22 atoms per centimeter cube. If you want to write that in MK system, then it is 5.85 into 10 to power 28 atoms per meter cube. So we got a value of Ns. Then let's find the value of Nv, which is, as I wrote here, Ns into exponential of minus EV by kT. Let us substitute the values. The Ns is 5.85 into 10 to power 28 into exponential of minus of 0.75 divided by k is 8.62 into into temperature is 773. So 5.85 into 10 to power 28 exponential of minus 11.26. And if you simplify further, you get 7.53 into 10 to power 23 vacancies per meter cube for the aluminium at 500 degrees Celsius. And that is the answer. Then let's go to the next sum. For unknown metal, the following data have been obtained. Let's see the data. What are the data given? Data, the row is given, density is given, which is 8.96 gram per centimeter cube, which is equals to 8.96 into 10 to power 3 kg per meter cube. So this is given. The structure is given. So structure is FCC. And so effective number of atoms per unit cell, which is N, equals to 4 for FCC. Interplanar spacing of plane whose Miller indices is 111 is also given, which is 2.08 into 10 to power minus 10 meter. And what we have to find is, we have to find atomic weight. And to find atomic weight, we also have to find lattice constant. So let us first find lattice constant. We know the relation between interatomic space, now interplanar spacing, and lattice constant, which is S square plus K square plus L square. In this case, the plane Miller indices is 111. So D suffix 111 is interplanar spacing of the plane 111. And this interplanar spacing is given, which is 2.08 into 10 to power minus 10 meter. And that is equals to A upon HKL is 111. So 1 square plus 1 square plus 1 square. And hence A is equals to 2.08 into root 3 into 10 to power minus 10 meter. And that is equals to 3.603 into 10 to power minus 10 meter, or 3.603 angstrom. So we got the value of A. Now once you know the value of A, we can find the atomic weight. The relation for that is A cube is equals to N into M divided by rho into Na, Avogadro's number. What we have to find is M here, atomic weight. So atomic weight is equals to A cube into rho into Na divided by small n, which is effective atoms per unit cell. A is known now, which is 3.603 into 10 to power minus 10 meter cube of this. Into rho is given. Let's see, rho 8.96 into 10 to power 3. 8.96 into 10 to power 3 kg per meter cube into Avogadro's number, which is 6.023 into 10 to power 26 per kg mole. We have considered here MK system divided by N. N is 4 because it is a FCC, and so N is equals to 4. If you simplify, what you get is 252.4 upon 4, and that is equals to 63.1 AMU. So atomic weight of the lead or unknown material is equals to 252 is equals to 63.1. Let's go to the next problem. From the following data, find out in what form chromium crystallizes. What are the given? Density is given, which is 7.19 into 10 to power 3 kg. Atomic weight is given, 52.01 AMU, and A is given is 2.88 angstrom, which is equals to 2.88 into 10 to power minus 10 meter. So these quantities are given, and we have to find what kind of structure it is, whether it is a simple cubic, BCC, FCC, or whatever. It means that we have to find the value of N, and to find the value of effective number of atoms per unit cell, we need the Avogadro's number, Na, which is 6.023 into 10 raised to 26 per kg mole. And the formula is same formula, A is equals to N into M divided by rho into Avogadro's number, or what we have to find is small n, effective number of atoms per unit cell. So that is equals to A cube into rho into Avogadro's number divided by molecular weight. A is 2.88 into 10 to power minus 10 meter cube of A into density is, this is the density, 7.19 into 10 to power 3 into Avogadro's number, this is the Avogadro's number, 6.023 into 10 to power 26, and these divided by m. M is the molecular or atomic weight, and that is equals to 52.01. Now the cube of this 2.88 is 23.89 into 10 to power minus 10. So I will just simplify this into 7.19 into 6.023 into 10 to power minus 30 of this plus 3 and plus 26. So this is nothing but 103.5 divided by 52.01, which is 1.99, and that is approximately equals to 2. So we got the value of N equals to 2. So the structure is BCC. So chromium crystallizes in BCC structure. That is the answer. Then let's see the last problem. In this, what we have to find is how many atoms per square millimeter are there on this 100, 110 and 11 plane of lead. Assume the interatomic distance to be 3.499 into 10 raised to minus 10 meter, and this lead has FCC structure. So the given things are, the structure is given, first the planes are given. In these planes, say 100, 110 and 111. In these planes, what we have to find is atoms per millimeter square. This is what we have to find for these planes. And interatomic distance is given. Interatomic distance, if interatomic distance is d, then that d is equals to 2r. D is the diameter, r is the radius of the atom. And these two atoms touch each other, so the distance between them is 2r. And this 2r is given, which is 3.499 into 10 to power minus 10 meter. This is given. Again, it is structure is given, which is FCC. So first I have to show you the 100 plane in the unit cell. So I am drawing 100 plane in the unit cell. Let's say this is the unit cell. I am going to need this, so I am going to copy this. So here this is FCC. FCC means there are 8 corners and 6 face center atoms, and for this I have to consider this 1000 plane. So this is the origin here. This is x-axis, y-axis and z-axis, and my 100 plane is, this is the plane. This is 1000 plane. In this plane, there are 4 atoms at the 4 corners, and this is the phase diagonal, and along the phase diagonal, atoms are in contact with each other. So maybe there's somewhere, this is the atom on the phase diagonal, they are in contact with each other. Because this is a FCC structure. So there are 8 corners and 6 face center. These are the 6 face center atoms. Now here we are considering 100 plane. 100 plane. And first, what we have to find is atoms per square millimeter. We have to find atoms per millimeter square. This is what we have to find. To find this, first what we have to find is number of atoms in plane. Now as you can see in this plane, there are four atoms at the four corners. These four atoms will be shared with, each one will be shared with another four planes. So contribution of each one to one plane is 1 by 4. So there is 1 by 4, total there are 4, plus there is one atom which is inside the plane. This atom, this is inside the plane, it is not shared with any other, and so there are effectively two atoms per plane. We got two atoms per plane. This is one. Second, we have to find area of the plane. Area of plane is, as you can see, area of plane. To find the area of the plane, atoms are in contact with each other along the phase diagonal. And so area of the plane here in this case is equals to a square. And the value of a, we have to first find the value of a. So to find the value of a, we know that atoms are in contact with each other along the phase diagonal. Phase diagonal is root 2a, and that root 2a is equals to 4r. We know the value of 2r. So this root 2a is equals to 2 into 2r. This 2r is given, which is interatomic distance. And that interatomic distance is, so 2 into interatomic distance divided by root 2, and that is equals to a. So 2 into interatomic distance is given here 3.499 into 10 raised to minus 10 meter divided by root 2. And if you simplify this, what we get is 4.95 into 10 to power minus 10 meter. Okay, this is the value of it. And the area is equals to a square. And a square is equals to 4.95 into 10 to power minus 10 square. This is the area. Then number of atoms, what we have to find is atoms per millimeter square, which is equals to atoms in plane divided by area of the plane. So atoms in plane are two atoms and area is 4.95 into 10 to power minus 10 square. And when you simplify this, what you get is 8.16 into 10 to power 18 atoms per meter square, because we have taken area in the meter, and that is equals to 8.16 into 10 to power 12 atoms per millimeter square. So this is what we got here. Then we have to consider the another plane. Another plane is 110. I have to show this plane. So let me draw the unit cell first. This is the unit cell. This is the origin, and this 1 plane is this is the 1 plane. Now this is FCC. So let me show the atoms to this 8 corners and 6 face center. This is one face center over here. This is another face center. This is all these 6 are the face center. But for this plane 110, as you can see, atoms per plane. There are 4 corners, 1, 2, 3, 4. Share of each is 1 by 4th. So 1 by 4th into 4 plus 2 are here. This face center, this and this 2. This one second. They are shared by 2 planes. So its contribution is half into 2, and that is equals to 2. So atoms per plane are 2. Then we have to find the area of the plane. Area of plane, suppose this is A, B, C, D is the plane. Then area of the plane is AB into BC. It's a rectangular, so AB into BC. AB is the face diagonal, which is root 2A, and BC is the edge, which is equals to A. So it is root 2A square, and we know the A. So this is a root 2. A is 4.95 into 10 raised to minus 10 square. So this is the area of the plane. Then we have to find first, let us say atoms per meter square is equals to atoms in plane 110 divided by area of plane. So atoms are 2 and area is root 2 into 4.95 into 10 to power minus 10 square, and that equals to 5.83 into 10 to power 18 atoms per meter square. We have to convert that into millimeters, so 5.83 into 10 to power 12 atoms per millimeter square. So this is what we got for 110. Then for 111 plane, So let us first draw the 111 plane. This is the unit cell, origin and plane. All the three sides of these planes are phase diagonal. Okay, if this is A, B, C. This is A, B, C is 1 plane in which this AB is equals to BC equals to AC, and they are phase diagonal, and which is equals to root 2A. So each side of this triangle is root 2A, and it is equilateral triangle. Let's show the atoms, and as I said that all these are the phase diagonal, so along the phase diagonal there is one atom. This is the atom of the back surface. So these are the three phase diagonals. If you want to show all, you can show, or just forget it. This is front surface, side surface. So first let's find effective atoms in plane. There are three corner atoms, and this is an equilateral triangle. It makes an angle 60 degree. So contribution of this ABC plane, ABC atoms to the plane are 1 by 6. So 1 by 6 into 3 plus 3 are phase diagonal atoms whose contribution is half. So plus half into 3, and that is 2. So effective atoms per unit cell are 2. Then we have to find area of the plane. So to find the area, what we need to know is the height of the triangle, this equilateral triangle. And height of equilateral triangle is equals to, height is equals to square root of AC square minus, let's say this point is the DC square. AC square, AC is root 2A. So root 2A square minus DC is root 2A by 2. So that is A by root 2 square, which is equals to 2A square minus A square by 2, and which comes to root 3 by 2 A square, or we can write root 3 by 2 A. So that is the height. And so the area of triangle is equals to half into side of the triangle into height. So half into side is root 2A, into height is root of 3 by 2 into a, and that is equals to 0.866 a square is the area. So what we have to find is atoms per meter cube, that is equals to atoms in plane divided by area of plane. Atoms in plane are 2. Area is 0.866 into a square. A is 4.95 into 10 to power minus 10 meter and square of this. After simplification, we get 9.43 into 10 to power 18 atoms per meter cube, which is equals to 9.43 into 10 to power 12 atoms per millimeter square. And this is the answer.